In the last section, we spoke about alcohols and some of their properties, and now we're going to get into some of the reactions that alcohols can undergo. One of those is called a dehydration reaction, and what you can see down here below is that chemical reaction that's happening, and it's dehydration because we're actually removing a water molecule from the alcohol. So we'll take the hydroxy group and an adjacent hydrogen from an adjacent carbon, and those are going to recombine into the water that's going to leave, and the electrons in there are going to then be put down into create this double bond. So we're actually going to create an alkene here from an alcohol after that dehydration reaction occurs. We can also, if we add an increased amount of heat, so this is what the delta means, is usually a heating chemical reaction that requires heat with the acid here above, the sulfuric acid. If we have excess ethanol, heat, concentrated acid, and heat, we can put this together and we can actually create now an ether. So certain conditions can also create an ether, or this might be a component that also comes out in a dehydration reaction. So this is also dehydration. We're removing water, but the outcome is different. Instead of getting an alkene, we're actually kind of fuse these two methyl groups together with an oxygen in the middle. So the singly bonded oxygen, but the oxygen isn't bonded to a hydrogen. So I'd like you to take a moment and look at this question. So if we have this compound, we have the 2-methyl-2-butanol, and we're going to want to determine what is going to happen in the dehydration reaction here. So remember, we're going to find, in order to name this, just to kind of go over naming too, we have 1 carbon, 2 carbon, 3, and the 4 carbon. So the 2-methyl part, that is that methyl group coming off. The 2-ol, the OL part, the butanol part, that is for the second carbon here on the hydroxide. So, and the butane is that 4-carbon backbone. So take a moment and figure out what is going to happen here. One of the things that we need to do is to look at the adjacent. We have to identify an adjacent hydrogen that we can remove. So we have these hydrogens that are going to be on primary carbon. So this is the carbon that's attached to the hydroxide. And then we have to have an adjacent carbon from which to grab our proton for interacting with the OH to create that water. So we know from the dehydration, we're going to get H2O out. Water is going to leave, which means we have to identify a hydroxide and then one of these other hydrogens. So there are two options. Really, these are all equivalent here, because there's a methyl group attached to both sides of that, and if we take that off, we're going to, if we take one of these, for example, then we would get something like this, where we would draw the double bond is actually going to be between this carbon that's in the blue and the carbon that's donating that proton. And it doesn't really matter. These are equivalent structures, really. We just have a difference in the conformation, but they're the same compound. If we kind of spin those things around, they are the same thing. And that's why these are equivalent protons over here. But if we do the proton that I'm going to highlight here, one of these protons, for example, which is also on an adjacent carbon, then we're going to get a different compound where we'll have something that will have that double bond now be between the number 2 carbon and the number 3 carbon. So number 2 and 3 here will have that double bond, and we'll still also have this kind of group up here. So this would be the original. These 2 carbons are still there, and we still have all the carbons that are located there, but now we have a double bond in a different location. So these 2 structures are different structures. Uh, so we'll have the water, one of those two structures, and that's the answer. Now, there's actually going to be a major and a minor product. This is going to be the minor product, and this is going to be the major product. We're not going to spend a ton of time on this, but this idea is called Markovnikov's rule. Russian scientists who studied this process who found out that the more substituted carbon is actually ends up becoming the more major product. So you see that double bond is inside and it's attached to more carbons, where this double bond or this double bond, that double bond ends on a carbon that's attached to two other hydrogens. There's just stability. This is more stable. And that reaction, we're not going to go into the details of the mechanism, but an intermediate is more stable that provides the kind of push towards the Markovnikov rule. So again, the more substituted carbon is going to be the one that between which the double bond forms. So we'll see that if we have the difference between a primary carbon or a secondary carbon, that secondary carbon, it's going to form between the secondary carbon or a tertiary carbon if that was an option. That's where the double bond is going to form preferentially. And just going back to this kind of idea with the carbon bond order between, if we're going to look at Markovnikov's rule, if we're looking at a primary carbon, secondary, tertiary, or quaternary carbon, obviously we don't have protons to pull off in a dehydration to allow for quaternary carbons to be involved in a dehydration. But if we're talking about tertiary, secondary, quaternary, if there is a choice, the proton's going to get pulled off from a tertiary carbon versus a secondary versus a primary. So there's an order that's going to happen, and that's what Markovnikov's rule is based off of. We can also get the reverse reaction to occur. So if we have an alkene, like we had ended up in the last reaction, and we have water, we can actually heat that up and increase the pressure to 60 atmospheres of pressure and add a phosphoric acid catalyst. We can actually hydrate that bond. We can add, basically what we're doing then is we're adding an OH to one side and an H to another, and that will provide now our hydration product. If we're looking at this kind of reaction, we're putting two things together. So this is actually an addition reaction where we're adding these two things together, and then we're creating one product. So two reactants to one product, that's an addition reaction. Another type of chemical reaction that alcohols undergo are oxidation reactions. So when we think about oxidation, remember the idea is the gain of electrons is a reduction and loss of electrons is oxidation. So this is the process we're looking at, is a loss of electrons for our compound of interest. This terminology here, this just means concentrated oxygen. Typically, it's going to be kind of pumped in oxygen, molecular oxygen that's going to be used in here. But a lot of times that bracketed oxygen means we're oxidizing our compound. And this is a very important reaction because it's seen in a lot of biochemical reactions and processes. And when we are actually going to be oxidizing, so if we look at sugar, if we have a compound that looks like this is kind of what our sugar looks like. And we have all of these alcohol groups on our sugar. We're going to essentially make CO2 out of it or something like that. And carbon dioxide, this is a very oxidized state of carbon. And throughout this process, we're actually going to, through biochemical means, generate ATP or energy. And so that is going to be a way that we can pull energy out of the system. So we're going to talk about that in a little bit. But let's look a little bit more closely at what is actually happening on this reaction. So what you'll notice is this carbon has a single bond to oxygen at the moment. And we are going to form now a double bond to oxygen with that carbon. And we're actually going to lose two of these hydrogen atoms in order to make that new bond. So we're increasing the number of carbon to oxygen bonds. So now let's look at, now that we can see what's happening in that, why do you think that oxidation would release energy? What is the system that, or what is happening here? What's the difference in these two chemical structures that would allow that to happen? Well, if we look at this setup right now, we can understand this by looking at electronegativity. So if we have between oxygen and hydrogen, the hydrogen is going to lose some of that electron density, and it's going to get pulled towards the oxygen. And also some of that electron density from the carbon is going to get pulled up towards the oxygen. The case on the right-hand side with the carbonyl compound, that C double bonded oxygen, it's the same thing. We have a partial negative and partial positive. Electron density is flowing up towards the oxygen. But now we have two sets of electrons in there rather than just one set. And what's happened now is that because electrons are going to pull closer to that charge of the oxygen has a smaller radius. And remember, if we're looking at the periodic table and that project you guys did where you looked at the size of the atom, remember atoms, as we move down to the right side of the periodic table, get smaller, and oxygen is smaller than carbon is. So that distance here, as we get more electrons in bonds that are associated with oxygen, that is going to change where those electrons are, and they're getting closer. These electrons are closer to positive charge. So it's kind of the idea of if you have a ball on the top of a hill, and what's going to be more stable, a hill that is really tall or a hill that's a little smaller. So if I have this would be the electrons associated with carbon versus electrons associated with oxygen. And when we have more bonds to oxygen, where we have actually electrons are closer, they're at a more stable state, they have a lower potential energy, and that's actually how this energy is kind of harnessed. We've removed some of that energy and we've organized it in a different way. So we'll talk more about that in terms of how this works biologically and biochemically, but that's the rationale for how this is working. So when we oxidize things and we increase our carbon to oxygen bonds, where typically there's some energy that's going to be released or harnessed during that process. Talking about different types of alcohols, right? We've just mentioned the primary, secondary, tertiary alcohols. Quaternary alcohols don't exist because carbon can't be bonded to 5 things. So if we're looking at a tertiary alcohol, we can't make more carbon to oxygen bonds because carbon already has bonds to other carbons. We can only change this if carbon has an attachment with hydrogen that we can remove. So in this instance, if we are under oxidating conditions, we have a tertiary alcohol, those will not chemically react because we can't make a double bond with carbon without breaking one of these other organic or carbon-carbon bonds, which isn't going to happen for an oxidation reaction. But we can look at different types of these alcohols. So if we look at tertiary alcohols, don't react. Quaternary alcohols don't exist. Secondary alcohols, though, we can make what's called a ketone. So this is the ketone functional group. These R's, remember, are different length chains of carbon groups. So when we have this, we can remove these hydrogens and then create this bond between a double bond between carbon and oxygen. And we have this carbonyl group is called the oxygen double bonded to carbon with within a chain. And this is the functional group called a ketone. So this is again through an oxidation of a secondary alcohol. If we have a primary alcohol, we start with that alcohol and it is at the end of a chain. So it's attached to 2 hydrogens. So we can do one reaction where we can create now what's called an aldehyde, and this is when it's that same carbonyl group, double bonded carbon to oxygen, but it's on the end of a chain and we have an extra hydrogen there. We can do an additional oxidation where we replace this hydrogen with an OH group, hydroxide group. So it's an alcohol functional group, but it's attached to a carbon that's already attached to a double bonded oxygen. And that's called the carboxylic acid functional group. So this can go through multiple steps of oxidation to give the final oxidized form of the carboxylic acid here. And the way we could further oxidize this would be to break this bond and allow carbon dioxide to form. That would be a complete oxidation. But typically with organic compounds, this will be the end state. We're not going to be able to get into conditions where we'd be able to break that carbon-carbon bond, at least in organic chemistry. But in biochemical means we are able to do that. All right, so what I want you to do is I want you to write out the products for the following oxidation reaction, and if there are major or minor products, and maybe there are multiple different versions of that. So kind of go back to the last couple of slides where we talked about the kind of reaction of the tertiary carbons versus the primary carbon, and what are some of the possible outcomes of this going to be. So next I want you to draw out the complete oxidation of ethanol that would be expected in someone who has consumed alcohol. So this is the methyl ethyl group, and then we have the OH group, which is an alcohol. So that is the ethanol. That's the same thing as ethyl alcohol. So I want you to draw out the complete oxidation of that compound. For this chemical reaction, what would happen is we essentially can look at drawing out, when we have the presence of oxygen, then we can look for the hydroxide and a hydrogen that's attached to that same carbon, and we're going to remove those hydrogens and make a double bond to oxygen. So we can kind of do this. We can keep everything in the same kind of orientation. I'm going to make a double bond to that oxygen. The hydrogens go away, and then I'm going to create a CH3 group here, and then hydrogen, these remain there. So that's the one step. But I still have another hydrogen that I can oxidize further, so I can add another amount of oxygen, and then we can also go to make this carbon, and I'm going to replace that the hydrogen with a hydroxide group, and then CH3. So this is our ethanol, and this is an acetaldehyde. We're going to talk about naming these in a minute. So this is an aldehyde functional group. It's a carbon double bonded to oxygen on the end of the chain. And then this is the acetic acid, or through IUPAC naming, ethanoic acid. The oic acid. And we'll talk about the naming of these, but these are some of the things that get produced during the metabolism of ethanol within our bodies. So there are enzymes that help do this in our bodies, where there's actually alcohol dehydrogenase helps to convert ethanol to the acetaldehyde, and then there's the aldehyde dehydrogenase 2, which helps to go from the acetaldehyde to the acetic acid. And this is essentially vinegar, completely harmless at the concentrations it would be at in our body and non-toxic. The acetaldehyde, however, isn't as great for us, and this is what generally, if you have too much ethanol and there's a backlog of this and you haven't been able to clear this from your system and help get this process going, this is what is going to give you a headache and a hangover, kind of feel cruddy if you've overconsumed alcohol. Now I want to talk about a special type of alcohol that's on a benzene ring, so these aromatic rings, and this is called a phenol. So phenol is just this aromatic benzene ring with a hydroxide functional group off the side of it. So alone, this is actually toxic, but it was used early on in the beginning of medicine as an antiseptic before people really knew about the dangers and how it was so toxic to people. But it was also helpful in keeping things from growing in wounds. And so there was kind of, at least it was safer at the moment than just cutting people open without using it. But more recently, safer phenolic compounds have been made as antiseptics. And this is an example. Resorcinol is also has the hydroxide functional groups, but it actually has a couple of them, and it has this hexane functional group off the side as well. And just as a note to naming and kind of looking at these different compounds, if we have a group on one side of this ring, remember that the adjacent carbons are ortho position carbons, and then the next group are the meta positions, and then we have the para position. So ortho is close, meta is in between, and para is on the other side of that ring. So if we're looking at, let's say this is our primary hydrogen or hydroxide group, it's at the 1 position, and we're going to this at the 1 position, 2, 3, and 4 positions, then we would say that the methyl ethyl propyl butyl pentyl hexane, that group ring here, is at the para position from the number 1 alcohol. The second alcohol is at the meta position from the number 1 alcohol. This numbering system also gives us the lowest numbers on our substituent groups, and we would also want, since alcohols are a priority group, those would get named first before our alkane group side chain. So the other way to name this is actually, this is kind of the commercial name, but IUPAC name is 4-hexyl 1,3-dihydroxybenzene. And again, this is fewer undesirable effects in this antiseptic, and it's often can be used in mouthwashes and lozenges as well for throat pain. We'll be talking about acids and bases a little later in for the next kind of set of lectures in the next week, but here we're looking at alcohols and phenols are slightly acidic, and that means that they can donate protons in water. So we can donate a proton and we can create this acidic or this protonated form of water, which is going to change the pH of the water because we're going to increase the proton concentration. And phenols are a little bit more acidic than alcohols. And again, these are just some of the properties of alcohols and phenols, is that they have this slightly acidic properties and they're able to release these protons. And again, the phenol is a little better than just a standard alcohol on a straight chain of carbon. And some of that has to do with the aromatic ring and the stability that this ion will have. Now we can allow the flow of this negative charge to be distributed throughout the whole ring, and that just provides some stability of this conjugate base. But again, we'll talk about that a little more in the future. As we're talking about some of the properties for these things, ethers, like we had spoken about, we can take 2 ethanols, and with the proper conditions, we can get these to fuse together to form this ether where the oxygen is singly bonded in this chain of carbons. And it's still a dehydration reaction, but we get a different product than a double bonded carbon groups. And these are, again, they're a little different. They're dipole. They have they're polar compounds, but they don't undergo hydrogen bonding because there's no hydrogen attached to that oxygen. It also can be used as a general anesthetic, and it's good because the effective dose, so typically you would look at an effective dose versus a lethal dose, and the difference between this 50 is basically 50% of, typically it's animal models. We're looking at 50% of those models see some result or effect of the dose, at a certain concentration, and the lethal dose is 50% of the animals die at that concentration. So if these, hopefully this concentration, the effective dose is really low and the lethal dose is very high, and that's very true for something like the diethyl ether, which is shown here, that is relatively safe because there's a big gap between these two different numbers. Okay, I want you to take a moment to look at these organic compounds, and based off of those functional groups that are available, which ones do you think would be have the lowest melting point, so take the least amount of energy to break apart the intermolecular forces, versus the highest melting point? So just take just a moment here, pause please, and organize these, think about this problem, and then I will walk through the solution. For these 5 different compounds, I've organized these based on their boiling points, and we're looking at 0 degrees Celsius for butane, and this is just a straight chain carbon group. As we have the cis or trans butane, we can, or butene, for example, it's a double bonded group now. We look at 1 to 4 degrees Celsius. So it's a little bit more intermolecular forces there because we have a bit of a more flattened out group, and they're able to interact more with those van der Waals forces. When we go to the methoxyethane, and this is the ether group, and we have, remember, polar bonds, so there's a difference in electronegativity differences between the carbons and the oxygen, and we get slightly positive charges on the adjacent carbons and slightly negative charge on here. So these charges allow these kind of to stack up and form those stronger intermolecular forces, which it raises the boiling point. So we have the dipole interactions that we can have here, versus just these would have the van der Waals. Here we move to hydrogen bonding, which, remember, is a special type of dipole-dipole that's stronger than a normal dipole-dipole because of that proton that's attached to a more electronegative element. We move up from 7.6, so we move up almost 70-degree difference there by adding that functional group. And then we add 2 of those hydroxides, and then we increase that even more. So we almost over double that because now we have 2 spots for that hydrogen bonding to occur. So those are some of the properties that I want you to know about in order to understand some of the differences and the interactions between carbon and oxygen and hydrogen within single bonds. And I'll talk more in the next section about aldehydes and ketones and carboxylic acids and the carbonyl functional group, and some of those reactions that we got out, remember, with the oxidation, some of those compounds, and we'll talk about those different types of compounds a little more in the next video.